Okay, folks, let's do part 2 here. You're going to hear some background noise because I am at the airport waiting to catch a flight, but I can think of no better time to record a lecture than while waiting to catch on an airplane, right? So, here's where we finished off. We were trying to get to the point to understand threshold voltage at a deeper level, and we had said one of the key things to understanding that was that if you want to go through any of these states for a MOSFET, you have to go sequentially through them back and forth. So I can't go straight from accumulation to inversion. If I want to go from accumulation, I need to go to flat band, depletion and weak inversion, and then to inversion. Okay? So let's look at these for a brief refresher. Here's flat band, right? Fermi levels line up, no voltage is applied, therefore there's no electric field across the oxide, lines are straight, and also there's no net charge on either side, right? Again, look over here, no net charge. The number of negative charges is canceled out by the number of positive charges, okay? Also, I want you to look in here briefly and look at how I draw the dipoles inside the dielectric. So here's a little bit of a zoom in of what they look like. I'm putting a positive and a minus, and then I might have another silicon dioxide molecule over here, positive, minus, and then another molecule here, positive and minus. So basically, you know, pretty much when you bond any two atoms, you end up with some sort of net dipole as they form a molecule, or portions of material inside something like silicon dioxide. Okay, and the key point is that these are polarizable. Now I can't really, these charges don't move; they're stuck with the molecules. But the molecule has a net positive and negative side, such that if I applied electric field, I might be able to reorient these a little bit. So if I applied electric field, you would find that these molecules might shift a little bit this way if I had a negative charge over here, and this one might shift a little bit this way to get its negative sign a little bit further away from the negative charge over here, and this one, if that's a negative charge, might also shift a little bit this way, bringing its positive charge closer and its negative charge further away. And so these can reorient a little bit, and that we'll find for a dielectric can help transfer charge from one side to the other. And so if a dielectric has a very high dielectric constant, high permeability, then that means its ability to sort of reorient charge like this and transfer charge across is much greater than a typical material. So let's look at accumulation here. Here's accumulation. I basically put negative voltage here. That raises the bands up, right? Negative charge associated with that. Positive charge showing up here as holes are accumulated. I've got electric field, so the bands have to bend for the oxide and for the semiconductor. Okay. Here's my voltage drop, negative voltage on this side, voltage drop across the oxide. We expect that because I can see this electric field, and then voltage drop across the semiconductor. This side's grounded. Okay. Now looking again inside here, you can see for these dipoles here that they reorient a little bit. And so if I look at how they've reoriented and transferred charge across the capacitor of the oxide, let's assume I have something, I'll draw it here. I've got negative charge here, and then that's on the metal, and then here's my oxide. Well, what happens is basically silicon dioxide molecules near the surface reorient a little bit, okay, such that they have their positive side here and negative side here. And then the next molecule sees the reoriented silicon dioxide. It reorients a little bit, positive, negative, and the next one, positive, negative. So you can see how all these molecules can basically rotate as necessary, just a little bit. They don't actually rotate this much, to line up their positive ends with the negative charge. Its next molecule is positive with the negative next, and this kind of feeds through the oxide. So now you're getting a glimpse in terms of how a dielectric works as well, in terms of negative charge getting to the other side and then showing up as positive charge on the other side. Because of course, on the other side of this dielectric, okay, this is the end of the dielectric, wrong color there, then I would start to see positive charge showing up over here, because if you look on this, I've got negative charge, I've got negative charge here, and so the positive charge is attracted to the negative charge. Okay, so that was accumulation. If I put a positive voltage on the metal, that pulls the bands down, and I should see a corresponding positive charge here and negative charge here. In this case, the negative charge is not due to electrons. Remember, this is lightly doped, so not many electrons come this way. But rather, I'm starting to deplete out holes, and as I do that, I leave behind these boron atoms which have negative charge. And so that's how I get my negative charge on the other side. But I still don't have a channel. If I keep applying more and more positive voltage, eventually I will see electrons start to show up. This is inversion, okay? And so let's take a deeper look at it. And let's revisit the this plot we had before, and let's make sense of it now. So this plot is plotting phi sub s, surface potential. This is the amount of band bending down here versus the charge I have at the surface, okay? So here phi sub s equals 0, meaning I've applied no voltage whatsoever. So of course I have no surface potential. And if that's the case, then I should have no charge on either side of the dielectric, right? So my charge goes to 0 here. Let's first look at accumulation. If I put a negative voltage on the metal, okay, then I'm biasing the MOSFET incorrectly, but I do get accumulation, and as I increase the negative voltage, I start to see holes increasing here at the surface. And so that's exponential, just like the Fermi distribution was for electrons as well. And so I can see this is a log plot, this is somewhat linear, and that's why on a log plot this is actually an exponential. As I put more electrons here, again, more holes show up here. Now, let's focus on what happens when we apply positive voltage to the gate, which gives us a positive surface potential. Remember, the first thing we said that happens is you deplete, right? So look what happens here. I apply a little bit of negative potential, and that turns into surface potential, which is the amount of band bending at the surface. And I start to see charge appear as I'm depleting out this layer and boron atoms are uncovered, okay? Now, mathematically, this is a square root function with respect to surface potential. And that should make sense because our depletion region width grows wider as the square root of voltage, right? And so if depletion region width grows with the square root of voltage, then the charge that I uncover should grow with the square root of voltage, and in this case the voltage is surface potential. Then at some point I all of a sudden start to see again an exponential increase in charge. Again, this is linear on a log plot, meaning that it's exponential, and that's inversion, where the electrons are showing up due to the Fermi level effective shift right under the oxide, and these are the ones that conduct and give me a MOSFET that has current from source to drain. So the thing is, we still haven't explained though, why do I need to get to 2 phi sub f before these electrons start to kick in? Why can't these electrons start to appear way out here? So what's this magical thing I need to basically shift the bands by 2 phi sub f? Well, look at it. You can see it right here on the next slide, okay? So what I've done here is I've separated both functions and I've mapped them out. So here's my depletion function, square root function, and it would just keep kind of going in this direction like this. And my electron growth is actually always happening. But look, here's if I project the electron, the growth rate for electrons through here, basically what happens is that my voltage is always feeding in, and it's always creating some electrons too, but the electrons don't start to take over until they surpass the mathematical growth rate for depletion charge. So I'm depleting with the square root function. Then all of a sudden what happens is that electrons start to appear, but they are able to generate charge exponentially. So the key point is that this function dominates over charge for depletion. And so what happens effectively is this function just goes away. So you get to a maximum depletion width, after which creation of electrons is a stronger mathematical function with voltage, and every additional positive charge you put here will then feed into creating electrons here. And it so happens that the point at which these curves cross over is 2 phi sub f. And so that's why we need 2 phi sub f to get to strong inversion, to start to create meaningful populations of electrons in the channel to get the MOSFET to turn on. Okay? So let's look at the charge and what it would map out in the MOSFET device. So here's my MOSFET, and I have this biased in inversion, in strong inversion. And understanding the charge here is important because it affects speed, because if you're charging a capacitor, that'll affect things in terms of RC time constant. It also affects how much power output I can get out of the device. The more charge I have, the more conductive the channel, the more source to drain current I can get. Okay, so let's look at this here. So I've got charge on the metal side. Here's Q sub n. This is my positive charge here, which shifted these bands down. And then you look over on the semiconductor side, and I've got two types of charges here. Okay, I've got a depletion charge, QD, and I've got an inversion charge, QN. QD is constant with distance because basically all the holes have been swept out here. And if my doping concentration here is constant, then the amount of charge I have across here is just the doping concentration. And so this is just showing that this is the boron atoms that you've uncovered, which have negative charge, and the number of atoms is constant as I move into the semiconductor because the doping for the semiconductor was constant. Then you look at the inversion charge, and it kind of spikes up and gets larger and larger as I get closer to the oxide surface. That makes sense because we said electrons are generated exponentially with surface potential. And so remember, if you look at my potential and the amount of bending that's happening here, it's small, it gets larger, and it reaches a maximum right here at the interface. And so most of my charge is right here at the surface, where most of the band bending occurs. As I go further out, the band bending's less, and then that inversion charge decreases. So the area of this and this and this, they should basically add up and counteract each other. Notice in the dielectric, there are no charges, which makes sense because that's the definition of a dielectric. Okay? If I plot my electric field for this, it would basically, there's no electric field across the metal because it's a perfect conductor, assumed in this. Here's my constant electric field across my dielectric, and then I hit my semiconductor, and the electric field decreases with distance. I can see that because my band bending is decreasing with distance. Steepest band, steepest E field, smallest slope, smallest E field, no slope, no E field, right? So, out here, here's a question for you. Why is Q0 when my position X is greater than the depletion width here? Well, that's easy. Remember, I know I have a ton of charges here in terms of holes, but for every hole out here, I also have a boron atom. So the number of negative charges and positive charges cancel out. My net charge is 0. That's why we draw it this way. Okay? And again, here's my voltage drop here as well. So, if I want to calculate my charges across here, again, my metal charge, QM, is equal to minus QD minus QN, because these are negative charges, right? So I put negatives in there, I end up with a net positive, okay? And I can calculate this as follows. QD is easy to calculate. It is basically Q, coulombs, the density of boron atoms, right, in my semiconductor here, and my depletion width, W. And so if you look at Q being, in this case, it's per centimeter squared, the units work out as well, and I end up with coulombs per centimeter squared as I multiply per centimeters cubed by centimeters here, and I get my charge density at the surface. Again, I want you to be careful with this. The channel width here is exaggerated in this little diagram. Typically, it's only about 10 nanometers deep, okay? So it's very thin, which makes sense because all the charge shows up exponentially at the surface, essentially. And our applied voltage, if you notice here, it's split across two things. The voltage is split across the insulator, so I've got voltage drop, VI, across the insulator being my oxide. And I've got the voltage drop across the semiconductor, which the total voltage drop is my surface potential. How much band bending did I have here? So there's surface potential coming back, okay? If you want to calculate how much voltage drop you have across the insulator, treat it like a capacitor. So the voltage drop across this capacitor is the capacitance, is determined by the capacitance and the charge Qi across it. So instead of Q equals CV, I have V equals Q, the charge on either side, divided by the capacitance, Ci. And so you can already see that VI is part of the price I have to pay for threshold voltage. I have to pay, part of the voltage I apply out here is dropped across the oxide and it's part of the price I have to pay to try to turn this MOSFET on. So the next thing we want to do is figure out how much depletion we need. So we have to pay for that, pay voltage for that too, right? So if I'm depleting here and uncovering charge, I just said that as I uncover charge, that charge turns into a need for applied voltage due to the capacitance of this, due to Q equals CV, right? And so if I can figure out how much depletion width and charge I need, I can use this to feed back into the voltage I have to pay again. So I can basically start with my width for a depletion region into a semiconductor. I have a metal on this side, which is like, it's the same as super heavily doped, so it's like having a heavily doped N side, which would simplify this down to the following equation, and my voltage in this case is surface potential. So my total voltage here applied is my surface potential. So this simplifies down here, and you might notice the similarity to Debye length. Okay, very similar equations compared to the Debye length which we had seen before. So, like a PN junction, the depletion width increases as we apply more voltage, right? And so you deplete further and further into the P-type material. But remember, we said eventually inversion sets in exponentially, and that takes over the charge increase as voltage is added. Therefore, the depletion region stops growing at a maximum value. So what's the maximum value? How do I know when that is? Well, that's when the surface potential will be equal to 2 phi sub f, right? When you hit 2 phi sub f, you start to get inversion, charges start to appear, and you get no more depletion. And so I will just substitute in 2 phi sub f in for surface potential. 2 phi sub f is this stuff. Put that in there, okay? And I'll put everything together, and now I have a nice equation which I can use to predict my maximum depletion width before inversion sets in. Again, key point, the depletion width maximizes. After that point, inversion takes over. It generates all the new charge because it's an exponential function, and the depletion width just completely stops. And so if you looked at this little plot over here, if I kept adding more voltage, I would get more and more inversion charge, but the depletion width would completely stop right here. It would not deplete anymore. So, we'd already shown this before. Depletion charge was the width times Na minus Q. We can substitute our new W back into this equation. Okay. I can also recognize that all this stuff in here is just phi sub f, and I can obtain my maximum depletion charge as QD max according to this. Okay. And so again, QD, if I have a W max, then I also have a maximum depletion charge calculated here. So this whole point of this exercise is to generate, determine an equation for threshold voltage. So how are you going to turn this into threshold voltage? Because threshold voltage is not charge. Well, again, let's use Q equals CV to turn this charge into a voltage. So now let's finally calculate our threshold voltage. So the first thing I want you to recall is that for a conducting channel, we need to have strong inversion. The surface should be made just as p-type as the substrate. The surface should be made just as n-type as the substrate is p-type, meaning I need to shift from this level of p-typeness to this level of n-typeness. So 2 phi sub f has to happen at the interface here. So I got to pay for that, and that's a potential, right? So this is already voltage. So to get the threshold voltage, we therefore need 2 phi sub f. Now, before we could get 2 phi sub f though, before we could get to inversion, we also had to max out the depletion region. And that creates a charge, and using Q equals CV, it means an additional voltage. So we had our QD max, which all we have to do to turn that into voltage is divided by the capacitance here. Now notice that I have a minus symbol outside of the front of this equation. That should make sense because I know that I have to pay a price to do this. I have to pay a price for 2 phi sub f, and I have to pay a price to deplete. So this should be positive to add to this to increase my threshold voltage. How's it end up being positive? Well, Q's negative, right? It is negatively charged boron atoms left behind here, and so I put a negative in here, and this term becomes a net positive. How do I calculate C sub I? That's easy. It's the dielectric constant of the oxide divided by its thickness. Because remember, QD is in units of coulombs per centimeter squared, so capacitance needs to be in units of farads per centimeter squared. in order to get the centimeter squared to cancel out and just give you volts in the end. So at this point, I'm going to show you a historical photo of some folks at Intel in its early days. Andrew Grove, which is at the far left, Bruce Deal in the center, and Ed Snow. And basically, look what they're doing here. They're showing how some of the MOSFETs work, and you see some very similar things to what we've talked about here today. So I just want to show you a little bit of historical perspective where a lot of this theory came from. So with that, how can we reduce our threshold voltage? If you look at this equation, you could see I don't want to have to pay for this, right? I would rather not pay this voltage and be able to get a lower threshold voltage for my MOSFET, right? Well, if I want to reduce the voltage I have to pay here, then I would like to increase my capacitance, which would bring this term down. How do you increase your capacitance? Well, there's only two things you can do. You can change dielectric constant, or you could decrease the thickness. But there's a limit to decreasing the oxide thickness. What is that? Well, at some point, if you get down to a few layers of silicon dioxide molecules, the chance for defects increases, but also tunneling and current increases. So basically, this doesn't act like an insulator, but rather you can get tunneling from the gate right into the channel, and that would be problematic because a MOSFET works assuming that you just charge up a capacitor, that you have no DC current flow at the gate. If you have DC current flow, then the power consumption for a thing like a computer chip would just go through the roof. So this is a beautiful TEM image of an actual MOSFET gate oxide semiconductor. Here's the gate material. Here's the silicon dioxide, 1.2 nanometers thick. Very thin to the point where you can start to get some tunneling current through here. You can see the actual individual molecules of silicon dioxide. And here's the silicon substrate. It's neat. You can see that nice crystal lattice of the silicon atoms perfectly bonded underneath the silicon dioxide. So the problem with this is that my dielectric constant is 4, and they ran into a point in industry where they couldn't make this any thinner. So what did they do? Well, what they did in industry, and this was a big deal, is they switched to something called high K dielectrics, such as hafnium oxide. And so this hafnium oxide has a dielectric constant of 18. So if you look at this, even though this is 3 times thicker, okay, so in terms of my equation, C is epsilon over thickness, even though my thickness went up about 3 times, right? Look at my dielectric constant. My dielectric constant went up much more than 4 times. It almost went up roughly almost 5 times. And so you can see the net effect is I get a net increase in capacitance. And the advantage here is that this is so much thicker that I don't have to worry about that tunneling current anymore. So this allows me to basically have higher capacitance without having such a thin layer that I run into tunneling current. This was a big deal though. When people went from this to this, it was very controversial. The reason why is that when you make these just few nanometer thick dielectrics, imagine a computer chip. If there was one defect here, one little crack or something like that, then the metal could penetrate through here, short to the silicon. If one transistor shorts out, the entire computer chip is shot, right? And so the key point is that if you want to make a perfect layer, that's easy to do with silicon dioxide because you start with this perfect silicon substrate, and all you got to do is basically rust it. You put it in the presence of some oxygen or water, and you get this nice little perfect thin oxide layer to grow into the surface. With something like this, hafnium oxide, you need to actually add it to the substrate, deposit it down, and your chances that if there's like a speck of dust or something on the surface that gets trapped in there and creates a defect, that increases your chance that you would lose a whole computer chip because of one little defect. So this was hard to do. This was not easy. Okay, so let's look at a couple other things before we wrap up. Why do we like to have small MOSFETs? People always talk about making MOSFET gate lengths smaller and smaller. We've talked about this before for MESFETs and JFETs as well. So basically, assume I have a bunch of transistors and I wire them all in series. If I look at my resistance, it's the resistance of the channel, and my capacitance is the capacitance of the gate. And so if I can reduce the width of my gate here, make it smaller, make a smaller transistor, then I reduce capacitance and I reduce the length of the channel, which reduces resistance. So when I basically put a voltage in here, current goes through here, higher current, lower R, feeds to the next capacitor, which has lower capacitance because the gate width was smaller, which then goes on to the next one, and basically the RC time constants add up, and that the whole circuit together gets much faster because the RC time constant for each one decreases, decreasing gate length, smaller C, smaller R. Both are advantages. If you look at a modern MOSFET, it looks like this. This is the gate, and you can see here's the channel, and you can see how much they've squished this in, that this thing kind of looks almost like an igloo or something, where they've really pinched in this to make the channel length as small as possible. So this is the gate material here, the oxides here, here's the channel, and they've made the distance between source and drain as small as possible. How are you going to tell different transistors apart? Well, we've looked at this before. Let's look at MOSFETs now. The key difference I want to emphasize is with JFETs, you had the current, you had the arrow here indicating that it's a reverse bias PN junction and showing you the direction for current if it were forward biased. With a MOSFET, you have no arrow. In fact, for a MOSFET, if you look in here, I draw a capacitor here. For a JFET, I didn't draw a capacitor. That's why you have a MOSFET. There's no arrow because it's not a PN junction, and you have this two parallel lines, which is a capacitor, because that's how you bias the device. Also, if you have PMOS, you've got the little dot here, which means instead of using positive voltage to turn it off, it's the opposite. It would be negative voltage. I'll show you later how you use these to make an inverter in terms of zeros and ones, but we won't cover that here today. Here's some MATLAB code. I want to show you when I generate. Take that MATLAB code, I get this very nice plot here of potential versus distance into a MOSFET. So this is my gate, here's my oxide, here's my semiconductor. Let's ask some questions as some review here. So why do I have zero slope lines on the left side here? Well, again, this is my metal. If you have a metal and it's high conductivity, there's no voltage drop across it, right? And so I have no electric field in the metal. Why do I have straight lines in the middle? Notice how straight these are. That's my oxide. Remember, the voltage, I have constant electric field across the oxide, so the potential drop should be constant as well. And this is for basically a bunch of different gate potentials. So I'm putting more and more negative voltage on the gate. That's what each one of these potential lines for. So here's minus 0.6 volts applied, voltage drop across the oxide, voltage drop across the semiconductor. Why do I have curved lines here for the semiconductor? Well, remember, if I looked at the semiconductor side, my bands have to bend, right? So if I had my oxide and I looked at my semiconductor, the bands are bent like this, right? I didn't do a very good job, but the key point is that here I have peak E field. You can see that here. And then as I go further and further out, eventually I get to this point where the semiconductor has no band bending and my change in voltage versus distance, or E field, goes to zero. Okay? Lastly, do you think this MOSFET has a high capacitance in terms of efficient gate dielectric or coupling of the voltage? What do you think, yes or no? Now, I'd say the answer is yes, because look at this. If I have minus 0.7 volts, this is how much voltage is dropped across the oxide. Only 0.1 volts. The rest of the voltage is dropped across the semiconductor. So this is a pretty good device in terms of very small voltage drop across the dielectric. Last question. Is this NMOS or PMOS? Remember, this is a plot of voltage, not electric field or band diagram energy. So I'm applying negative voltage to the gate. If I'm applying negative voltage to the gate, that means negative charge, meaning that on the opposite side of the dielectric, I'm generating positive charge. That would mean a P-type channel. This is a PMOS device. Last quick topic. I showed you a picture earlier with Andy Grove at Intel. I have some really strongly recommended books if you're interested in looking for some reading material next time you have some break. Andy Grove was Time's Man of the Year in 1997 for all the fantastic things he did to make Intel what it is today. This is a great book in terms of how he turned Intel around and made it into the company it was today. Basically, it was ready to go under. And he fought to push Intel into this unknown area of microprocessors, which people didn't even know if there was much of a market for it. But he had some great vision in terms of where it could go. So you read that, Read about all his success in terms of making Intel what it is today. And then I want you to read this book, Swimming Across. This is basically about his whole life just getting to the point where he could start to study to be an engineer in college at the City College in New York. And so it'll remind you how fortunate you are to be here as an EE, because he had an incredibly difficult time just staying alive as a child in Nazi-occupied Hungary, getting to the point where he could finally make it to school in the U.S. And the last thing, one other book I recommend for all engineers is Good to Great. You're all going to be working for a company at some point. This tells you how to find good companies to work for. Good companies will follow the principles in this book, and it's also a very good read and a classic read for anyone in most companies. Okay, that's it. Let's do some review. So the depletion, I created the oxide maximize. Why does it maximize? So this depletion grows, but then it maximizes. Here's your hint. Once my surface potential is above threshold voltage, at what mathematical rate are carriers generated in the channel? Look back at that Q sub S plot and think about how we calculate carrier concentration. Here's a key thing I want to correct. We'll see next lecture, however, that surface potential and external gate voltage are not proportional. So in the part 1 lecture, I said that if you apply gate voltage, you'll see an exponential increase in carriers in the channel. I misspoke. That's actually not correct. The exponential increase in carriers here is with surface potential, but gate potential does not equal surface potential. So we'll talk about that next time. So I just wanted to fix that small error. Why don't we see strong exponential increase in carriers until the band bending phi sub s reaches 2 phi sub f? Again, see the Q sub s plot. How does MOSFET gate voltage change if I reverse all the doping types? That should be easy. Why can't I make the oxide thinner and thinner? Just one word for that answer will do. And why do smaller MOSFETs make faster chips? Look at that slide on RC time constant. It should all make sense. Keep in mind, though, that computer chips aren't getting faster today. And the reason why is that they could be faster, but they've got so many transistors packed in such a dense area and they're running them so fast, they can't get the heat out. And so that's the biggest limit for microprocessor speed today. That said, they're still trying to make them smaller because they can fit more computing power in a given area, more logic operations in a given area of computer chip.